All right, here we go. Lesson 1.2.1. So we're in section 2 of chapter 1. What we're going to do in this part is we're going to formalize some of the relationships that we're looking at. When I say formalize, I mean like my sister calls me Maddie and I call my sister Shaw. But when my parents were mad at us, instead of calling me Maddie, my mother would call me Matthew Ray Holcomb. That's my formal name. Or they'd call my sister instead of Shaw, like I call her, they say Shelley Louise Holcomb, the formal name for it. We're going to kind of get a little bit formal in how we refer to our relationships between the X values and the Y values. Kind of building off what we've done before in the last lesson, we're going to be looking at relationships between the inputs, the X values, and the outputs, and make equations from them. So when we're looking at this one, you always want to look at how the changes are happening between them. So we want to see, is there a relationship between the X value and the Y value? Is one of them changing the other one, or are they related in some way? So I'm looking at the Y values first because the X values are just increasing by 1 each time. But the Y values from -4 to -1 looks like it's adding 3 here. And from here to here, it's adding 3 more. And it looks like every single time it's adding 3. So that would be kind of like tile pattern 1 from last time, where it was increasing by the same amount each time. We said we saw that made a graph that was linear. So each time the input increases by 1, the output increases by 3. Now, if we want to make an equation for it, we'd say the Y value is equal to, all right, now I have to have an equation with the X input in it. So we're going to put the X somewhere. So X has to be here somewhere. But we also want to look at where are we starting. And we usually start with the X value of 0. So that's kind of like our starting point. So at the X value of 0, when there is no X, 0 for the X, it looks like our value is -1. So when there is no X value, our value of Y would be -1. So here I've got an equation, Y equals X minus 1. And if I plug in 0, it works. If I plug in 1, 1 minus 1 is 0. That's not 2. So my equation doesn't work right now. So what do I need to do to the X value to make this work? Well, we said down here the Y values were increasing by 3 each increase of 1 up here. So if I put a 3 right here, the first value still works for 0 and -1. If I plug in 0, 3 times 0 is 0, and I get -1. But now let's see what happens when I plug in 1. When I plug in 1, 3 times 1 is 3, and 3 minus 1 is 2. So my function, my equation, looks like it's working. If I plug in 2, 3 times 2 is 6, 6 minus 1 is 5. So it's working out. Even works out for the negative numbers. If I do 3 times a -1, that's -3. -3 minus 1 is -4. So it looks like I've got the right equation here. So we're going to look at our starting value, the X value of 0, the Y-intercept, which is -1. So that's where I got this number from. And then I saw it was increasing by 3, and that's where I put that 3x from. All right, now we're going to get a little bit formal, a little bit more formal than what we've done before. We're going to look at something called function notation. And function notation, you'll notice, is slightly different because of this right here, f of x. You might have seen that before in other math classes. But the way that we say that is f of x. So f, and then the parentheses x, means f of x. It means that our output is a function of, or it's related to, the input. You can also think of this as being independent and dependent. The X value we usually say is an independent value, meaning that it doesn't depend on anything. It can be whatever it wants. The Y value, however, is what we would call something that is dependent. the y value cannot be whatever it wants. It depends on whatever you plug in for the independent quantity, the x value. So the x value goes out, and whatever goes in for the x value, what comes out is dependent on it. So that's our function. So when we write the function notation, this is like a formal way of saying it, and saying the f of x, that's just going to represent our y value. It's saying that the output is dependent, or it's a function of, whatever you input. So f of x means it's a function of whatever you put in. So your output is a function of whatever you input. Now, there's other reasons other than just renaming it. There's some other reasons why we might do this. Let's look at that first lesson that we had here. Here we had a whole bunch of these other functions that we did before. And if I wanted to refer to one of them, I would have to say, okay, this is the function x minus 2 squared, and this is the function 4x minus 32, and this is the function 1 over x. But when we have function notation, I could say, this is f of x. And maybe I call this one g of x. And maybe I call this one h of x. So then when I say, okay, I'm talking about f of x, everybody goes, okay, that's that one. And when I'm talking about g of x, oh, that's that one. And when I'm talking about h of x, oh, that's that one. So it's a way to name the function without having to state the entire equation of the function. It's a really quick way to say, hey, let's talk about g of x. Oh, he's talking about this one over here. Let's talk about h of x. Oh, it's this one over here. So it's a way that you can really quickly refer to equations without having to state the entire equation. So this is just a formal way of doing it. So in this function notation, we'll see here that on my input, my independent quantity is 3. I put it into the function. The function multiplies that by 3 and subtracts 1. So I do 3 times 3 is 9. 9 minus 1 is 8. So we say that the output is a function of the input, or it depends on what you put it in. So this one says, not anymore does it say f of x, it says f of 3, because our input was 3. So our function, when the input of 3, equals 8. So that's what the function notation means. So let's look at here. We're going to find f of 14. What this means is I want to know what the output is going to be when the input is 14. So if I plug that in, I'd say, okay, 3 times 14, and then I would subtract 1. So 3 times 14, I think, is 42. And 42 minus 1 is 41. So f of 14 is equal to 41. So the output, which is dependent on the input being 14, is equal to 41. So f of 14 equals 41. Now let's look at the next one, f of negative 10. So f of negative 10 means that the x value is negative 10, and f of negative 10 means I want to find out I want to find out what the output value is going to be when the input value is negative 10. So I do 3 times negative 10, because my function is 3x minus 1. So 3x is negative 10, and minus 1. So here I've got 3 times negative 10 is negative 30, minus 1. Looks like I get negative 31. So f of negative 10 is equal to negative 31. There's my output. So my input is negative 10. It goes into the function, and then it comes out as negative 31. All right, what if we knew that f of x was equal to 24? What should the x value be? So basically what we're saying here is we know what the y value is, and we want to know what the x value is. So our function is f of x equals 3x minus 1. So we're saying f of x is 24. So instead of f of x, I'm going to plug in 24 equals 3x minus 1. So all I have to do is add 1 to both sides, and I get 3x is equal to 25. And then I'm going to divide by 3. So I divide by 3, and I end up with x is equal to 25 over 3. So you can just leave it like that. I would prefer if you leave it like that, but if you wanted to plug it into your calculator and see what 25 divided by 3 was, you would get like, what's that, 8.3 repeating or so? But it's just better to leave it as a fraction here. So our x value would be 25 over 3. All right, so we've got our function notation down. We know that that's called f of x. It just means the y value. So f of x and y are the same thing. It's just a more formal way to look at it. All right, let's look at our next one. Our input is x, our output f of x or y. And it looks like on this one, we have an incomplete chart. So let's look at the complete sections. When you plug in 1, you get 1, okay? Over here, when you plug in 49, you get 7. When you plug in 25, you get 5. It looks like I'm getting a smaller number most of the time when I plug in the input, so it's getting smaller somehow. But is there a relationship between 1 and 1, 49 and 7, 25 and 5? I have to kind of think through this one. It's a little bit tough, but there is a relationship between those. Look at it. 7 squared is 49, 5 squared is 25, 1 squared is 1. So it's the opposite of the squares. Well, what's the opposite of squares? Square rooting. So it looks like this is a square root of x. So if I plug in 1 here, the square root of 1 is 1. If I plug in 49 here, the square root of 49 is 7, because it's the opposite of squaring. If I plug in 25 here, I get 5. So finishing these off, what's the square root of 9? It's 3. What's the square root of 100? It's 10, because 10 times 10 is 100. What's the square root of 4? It's 2. If I wanted to go backwards, I would square it instead of square rooting. So this would be 16, because what's the square root of 16? It's 4. What's the square root of 0? It's 0. What's the square root of 20? Ooh, square root of 20. I might need a calculator for that, because I know that the square root of 16 was 4, and the square root of 25 is 5. So root 20 has to be between 4 and 5 somewhere. I'm not quite sure what that is. And you can plug it into your calculator, and it is approximately 4.5. The number actually goes on forever. It never stops. It's an irrational number. You'll find more about that later. But if you plug into your calculator, if you round it to the nearest tenth, it comes out to about, that's what the two squiggly lines mean, about 4.5 or so. All right, moving on. All right, I've got all these lovely little functions. You might have to blow up your screen. I didn't know this would be this small. But anyways, we're going to fill out the rest of these. So this one, the function is a negative 2x plus 4. The input is a negative 3. So I'm going to say, okay, it wants to know the output. So I'm going to do negative 2. The input is negative 3 plus 4. So negative 2 times negative 3 is 6. 6 plus 4 is 10. So f of x is 10. Next one, the input is 2. The function is 3 times 7 to the x. Ooh, that's tricky. All right, so 3 times 7, and then x is 2. So I have to do my order of operations. I would square 7 first, that's 49. And 49 plus 3 is 52. Oh, 49 times 3, not plus 3. What was I thinking? So 49 times 3 should be 147. I caught my error before I made it. Nice. All right, next one. We don't know what our input, this is a question mark right there. We don't know what our input is, and we got x to the third. If this is too small, just open up your book, because this is straight from your book. So anyways, over here, this is x to the third, and I don't know what my input is, but I know my output is 125. So I have to think, I have to go backwards and say, okay, what number multiplied by itself 3 times is 125? Well, 5 times 5 times 5 is 125, so my input must be 5 for this one. For D, it looks like we're going to take the square root of x and then add 1. So I'm going to plug in -2. So the square root of x, so the square root of -2, ooh, that's a little bit of a problem. Because remember what we said before, square rooting was the opposite of squaring. So what number multiplied by itself equals -2? Well, we've already seen on previous lessons that any time that you multiply a number by itself, it's positive, not negative. So this is impossible. There is no number multiplied by itself that equals -2, at least not a real number. So we're going to have to say that this is not possible because you cannot take the square root of a negative number. So there is no output. It is impossible to have a square root of a negative number and let it be real. You'll see later on in other classes that it's possible to have imaginary numbers, but we're going to just deal with real numbers for right now. And that's just not possible. No output. All right, next one. We've got a fraction here. We've got x plus 3 over 2x minus 5. I know this is small. Again, use your book. So I've got x plus 3 on top. So I'm going to plug in x, which is 2, plus 3. In the denominator, I've got 2x minus 5. So I'm going to do 2, and x is 2, minus 5. So on top, I get 5. On the bottom, the denominator, I've got 2 times 2 is 4. 4 minus 5 is -1. So 5 over -1, which is just -5 for that one. All right, moving on. And the next one, my output is 99. So I've got x squared minus 1, and then it's getting to 99. So I want to know if x squared minus 1 equals 99, what did x have to be? Well, the first thing I'm going to do is add 1 to both sides. So x squared is equal to 100. And then I'm going to say, okay, so what number squared is 100? And you might say 10. And you would be correct, but you wouldn't be wholly correct. There's another number that if you square it, gives you 100. Can you think of it? It's -10, because -10 times -10 is positive 100. So this one has 2 input values that would give you the same output value, 10 and -10. All right, we got an absolute value problem, and we kind of went over absolute value before. And this one says the absolute value of some number happens and you get a -3. But what do we learn about absolute value? We learned absolute value is always positive. So there is no input value that would give you a negative number because we're going to take the absolute value. The absolute value of x cannot be equal to -3 because anytime you get an absolute value, it would be positive, not negative. So there are no x values. Okay, next one, we're inputting 4, and the function is 1/2 times 3 to the 4th power. Let's see, 3 times 3 is 9, times 3 more is 27, times 3 more is 81. So this is 1/2 times 81. And we can just write that as 81 over 2. Can you write 40.5? Sure, go ahead. I would just leave it as 80.2, 81 over 2. Last one. We're going to plug in -4. So we're going to do the absolute value of -4, and then we're going to subtract 2. So absolute value happens first. So this is 4 minus 2, and then 4 minus 2 is 2. So our output value is 2. All right, we are moving along. We're almost done here. Let's do our next page. Where did I put it? Here it is. All right, so those were all functions where we were looking at the actual equation of it. Now we're going to just look at graphs and see if we can find the same information on this. So on this graph here, the graph is called g of x. So that's just the name of that graph, g of x. So the input value is 2, and we want to find out what the output value is. And according to this, when you input 2, the output is 5. Now you can actually find this on the graph. The input is the x value, so here's 2, and if you go up 1, 2, 3, 4, 5, there's the output value of 5. So when you plugged in 2, the output over here is 5. Plug in 2, get 5. It's on the line. So the next one says, okay, I've got g of 1, and I want to find it. So that means my input value is 1, and my output value looks like it's also 1 right here at this point. So input 1, output 1. X is 1, y is 1. So I would get 1. G of negative 1. All right, so negative 1, I'm going to go over here. Negative 1, I go down to the line here, and it looks like we've got a value of negative 1, 2. So when I plug in negative 1, I get negative 2 over here on the graph. G of 0. G of 0, that's when x is 0. So x is 0 gives me this point right here, which is a y value of negative 1. All right, part C. G of x is negative 2.5. Ooh, let's find that. So that's a y value. So here's 1, 2, 2.5. Beep, 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 beep. So negative 2.5, I want to find out what the value of x is going to end up being. So we're going to find out what the value of x is when we get negative 2.5. So if we go back there, negative 2.5 looks like it crosses right about here-ish, something like that, pretty close. So about negative 2. So the x value would be negative 2 for that one. So we went to negative 2.5, looks like right there it's matching up, so negative 1 is the x value. Is there more than one answer? No, because the graph doesn't cross here at more than one point. So no, there is not more than one answer for that. Now. All right, so we can do it from an equation, or we can even do it from graphs. So remember, we're trying to see if we can do it from equations, graphs, tables, and situations, and we're trying to go see how they're interrelated, go from one to the other. All right, our last section for this is our methods and meanings. So you're going to want to write this in your notes. Don't just think that I'm showing you a picture. It's also in your book, but it's nice to have all of these things in one place. The next thing we're going to look, we looked at angles last time. We're going to go a little bit more into angles. And we know that complementary angles are angles that together add up to 90 degrees. So here I've got this angle, I'll call it angle 1, and this angle over here I'll call angle 2. We see that angle 1 and 2 are right next to each other, and they make up the one big 90 degree angle. So those would be complementary. We would also call those adjacent because they're next to each other. Over here, we've got this angle over here that's 40, this angle that's over here that's 50. They're not next to each other, but they still add up to 90, so we would also call those complementary angles. So they don't have to be next to each other to be complementary, they just have to add up to 90. And then supplementary angles are angles that add up to 180 degrees. So again, they can be not next to each other, so non-adjacent, so 60 and 120, that makes 180, or they can make a straight line, and we found out that straight angles were 180 degrees. So here's angle 3 and angle 4. Those two would be supplementary angles because straight lines are 180, and these two angles together make 180 degrees. So complementary 90, supplementary 180. If you forget which one is which, just think of it as being alphabetical. C comes before S, 90 comes before 180. Okay, vertical angles. Anytime that you have two lines that cross each other, you come up with angles on opposite sides. Those ones we call vertical angles. And we find out later on that vertical angles are always equal to each other. So here we see that C and G would be equal to each other, and also F and D would be equal to each other. They'd be the same measurement. Next one, we've got corresponding angles. Corresponding angles is when we have parallel lines, and we call this a transversal line going through it. Now, they don't have to be parallel to be corresponding, but in order for them to be congruent in this situation, they're going to have to be. So I got parallel lines here. So what would be a corresponding? Corresponding, so here's my transversal. Corresponding is on the same side of the transversal. So you can see here that D and M are on the same side of the transversal. Those two angles we would say are corresponding. Now one is inside of the two lines, so we would call this the interior, and one is outside the two lines. So D and M are corresponding. Same side of transversal, one's outside, one's inside. And we find out that if these lines are parallel, D and M would be congruent to each other. Now, there are other corresponding angles on here. F and K would be corresponding angles because they're on the same side of transversal. This time they're on this side, and one is inside and one is outside. There are more. C and H would also be corresponding angles because they're on the same side of the transversal, and C is on the outside and H is on the inside. And then G and N would also be corresponding angles because G is on the inside, N is on the outside, and they're on the same side of the transversal. That means they would be congruent. So if the lines are parallel, those angles are congruent. Next one we have is alternate interior angles. So we got our two lines and our transversal again. These lines are parallel because when they're parallel, these alternate interior angles can be congruent. And we see that F and M are alternate interior angles. Alternate means different sides of the transversal. F is on this side of the transversal, so L's are transversal, and then M is on this side. And they're both interior angles. So those would be alternate interior angles. There's another pair of alternate interior angles. G and H are also alternate interior. Alternate meaning different sides of the transversal. Interior meaning they're between those two lines. And if these lines are parallel, those would be alternate interior angles and they'd be equal to each other. All right, that's all you got. Enjoy. Bye-bye.